you should drive it to the gas station. We should put air in the tires like that.
Hard in here. Oh, I can order. I've got the whole thing so far, a minute 15. Oh, yeah, I don't like this. I won't
Everybody's looking out their windows at this thing.
Yeah, they're like jumping balls. I want that.
Well, I'm not showing it that well. I wouldn't do it with the computer on. Yeah, I mean, we can, hold on. I can just...
You put that on. All right, go.
So, good evening, all the participants. I'm very happy to welcome you all on behalf of SEEK. We are in the second International Faculty Development Program and the webinar online. And we have a very, very special guest today. And before going into the webinar, I would like to brief about the theme of our webinar and the guest. So Industry 4.0 is the theme of our webinar, and it is the digital transformation of manufacturing, production and related industries and the value creation process. Industry 4 is used interchangeably with the fourth industrial revolution and represents a new stage in the organization and the control of the industry value chain. For 125 years, the automotive industry has been a force for innovation and economic growth. Now, in the early decades of the 21st century, the pace of innovation is speeding up and the industry is on the brink of a new technological revolution, that is self-driving vehicles. The new technology could provide solutions to some of our most intractable social problems: the high cost of traffic crashes and transportation infrastructure, the millions of hours wasted in traffic jams, and the wasted urban space given. But if self-driving vehicles become a reality, the implications would also be profoundly disruptive for almost every stakeholder in the automotive ecosystem. Anyway, I'm just eager to see what Jim is going to have today. Let me share the introduction screen of him. So this is our international online faculty development too. We have 5 days, and the first day, that is today, we have James Conrad. And Jim, he's a professor in electrical and computer engineering, UNC Charlotte. James Conrad received his bachelor's degree in computer science from the University of Illinois, Urbana, and his master's and doctoral degree in computer engineering from North Carolina State University. He has worked at IBM, Ericsson, Sony Ericsson, and BPM Technology. And he has served as an instructor at North Carolina State University. And he has also served as an assistant professor at the University of Arkansas. And he is currently a professor at the University of North Carolina at Charlotte. And his research areas are computer engineering, embedded systems, robotics, and computer architecture. And he has memberships as he's a professional engineer. He's a senior member of the IEEE. He's a certified project management professional and a member of Eta Kappa Nu and the Project Management Institute. And he's held a lot of positions in IEEE, and the most important and prestigious positions as IEEE Board of Directors, as Region 3 Director for 2016 and 17, and Director in 2020 when he was also serving as IEEE USA President. And he is the author of numerous books, book chapters, journal articles, and conference papers in the areas of embedded systems, robotics, parallel processing, engineering, education. And the university has provided ATV for James and his research students to make into an autonomous vehicle. I don't know whether Jim is doing a test ride or a joyride. And the University of North Carolina at Charlotte, USA has converted an off-the-shelf all-terrain vehicle, ATV, from a driver-controlled vehicle to an autonomous vehicle. And the UNC Charlotte is working on autonomous all-terrain vehicle that can sense its environment and traverse most any terrain. And I would like to throw back the memory where first I met Jim in India. And also he had addressed our students. We had a wonderful session with Jim. And do you remember this, Jim? I had clicked your picture.
Actually, this picture is at the end of my presentation.
I really enjoyed the way you were admiring Indian culture, and as soon as you saw this, cow in Mahabalipuram, I could still remember the expression, and you wanted to go and touch and talk to that. Really wonderful memories I do have with regarding your visit. And Jim is, I feel that you would have been born in India in your last birth, Jim, because you're so associated with India and you keep coming, visiting colleges, visiting a lot of places. And that's really wonderful to have you today at our session. And I would like to wholeheartedly welcome you and take over the session.
Thank you. I believe all of you can hear me, so I will go with that. And I will now share.
You can be a little more louder, Jim.
Oh, can you not hear me good enough?
Oh, it's fine.
All right. So I'm assuming you can see this slide.
You need to share it.
Oh, I need to hit the button that says share. There we go. How about that?
Yes.
All right. Thank you very much for being here during this talk. I hope to not have it so much of a lecture as it is a discussion. And so if you have at any time any questions, I do have the chat window open, and I will feel free to ask questions, and I'll answer those questions as we go along. So the basic agenda is a little bit of discussion of who am I, what's the initial problem definition, And then this all-terrain vehicle project, I'm going to take through the 3 phases, and then at the end we'll have discussion and conclusions. But the important thing to note is that when we first started this, everything was controlled with specifically programmed computer instructions. We're getting to the point now where we realize that, you know what, you're going to need machine learning to be able to do anything, because this is getting more and more complex. And in fact, that's one of the evolutions of Factory 4.0 is there's going to be a lot more artificial intelligence and machine learning that's going to be needed to do any of this work. So without further ado, this is me. I got a wonderful introduction all the way at the beginning. One thing that I was not mentioned was that I am also an ABET evaluator and a ABET consultant. So I have been to India 2 times to review programs, academic programs for ABET. Actually, I've been to India now 6 times. My most recent time was, of all things, at the beginning of March, before the whole world fell apart. And it was a wonderful visit. I got to finally go to the Taj Mahal for the first time. So if I had a really good computer, I would be putting the Taj Mahal behind me. But unfortunately, my computer is a little bit underpowered. So I think we'll just go with my home. So to give a little bit of background, I started my work with embedded systems at UNC Charlotte. My industry, which I had spent about 14 years in industry, was all concentrated in the areas of embedded systems. Everything from display products, communications products, into indoor mobile phone systems, and then cellular phone systems themselves. So when I moved into academia from industry, I worked with companies, and since I understood the world of manufacturing consumer products, and so I'm able to teach and graduate students, research students, in all sorts of different embedded system fields, everything from again, communications all the way through robotics. And I actually have, as you see here, some students working at all places like Tesla or IM Robotics, iRobot, as well as TI, Qualcomm, etc. And in fact, for what it is worth, I counted this all up. I have graduated over 130 master's and PhD students, of which 110 of them were from India. So I do understand the Indian system. Some other areas of expertise, we work a lot with microcontrollers and microprocessors, Atmel, Renesas, Microchip, Cypress, Xilinx, Texas Instruments, all sorts of others, and as well as the software systems and sensors. Now, to that degree, I've gotten more and more into autonomous robotics. Specifically, let's think about the technologies that you will need for designing the systems, the control systems, as well as maybe localization and mapping software and systems needed. One thing I don't necessarily do a lot of, and that is the creation of the mechanical platforms. I pretty much assume that I am going to take an existing mechanical and sometimes mechanical and electrical system and augment it. And so my concentration is more on the computing systems to control all of those robots that we build. And yes, if you are interested, I am the Stakedo guy. Back in the late 90s, early 2000s, I worked with this small little robot called Stakedo. It's very similar to a walking stick, which is a type of bug here in the U.S. I'm not sure if it's a bug there in India. I never saw one. But the whole idea is that we published 3 books, and the books had instructions on how to build this robot, and inside the book were all the parts to build the robot. The third book was eventually one controlled by a microprocessor, a Texas Instruments MSP 430. So if you go out there and you do a search on Staccato, you'll see the books, and you'll probably see my main name associated with it. So before I start talking about my robotics project, I wanted to actually back up and take a little look at what is a robot. And so the best way to look at this is the ISO definitions of what a robot and what autonomy is. So specifically, when we're talking about the standardized definition, it is a actuated mechanism programmable in 2 or more axes with a degree of autonomy moving within its environment to perform intended tasks. This is the 2012 version. I have not checked in the last 2 years to see if they had updated that, because I think they are looking at that, because there's also an updated definition that a working group was looking at, and which they changed it a little bit. Programmed actuated mechanism with a degree of autonomy. Now they're talking about that a robot needs to have a degree of autonomy, and not necessarily how many axes that it works. But look at that, moving within its environment to perform intended tasks. Very similar to the one above it, but they've taken away the requirement that it needs to have 2 or more axes. So they also define autonomy, ability to perform the intended task based on current state and sensing without human intervention. And so that's an important aspect of all robotics as we go forward, is that we're going to be looking at systems that will do some sort of intended task, but you need to have at least some sort of pre-programmed reaction based on sensor readings, or you need to have a system already built in that has pre-learned different reactions to the sensor readings. And pre-learned would mean something along the lines of machine learning and artificial intelligence. By the way, they also have different definitions of what a service, industrial, personal care, or medical robot is as subsystems. And as a matter of fact, I've defined some of these right here. Service robots, they're going to perform useful tasks. And if you think about the ones I have on the screen right here, this butler-like robot I've actually seen work in, let's see, people cannot hear me, so I'm going to try my best to fix my microphone. Let's see if I could.
No, you can just raise your voice. That's enough. You don't have to worry about it.
Okay. I'm actually talking rather loud. So I'm going to see if I can. Man, and it is already pushed up as high as it could go. All right, so I will just talk a lot louder. How about that?
I think the speaker volume, is it for your side? The one which is above?
Yeah, my microphone side is as high as it can go, and as it's reading it, it's identifying that it's pushing it up to the max. And I'm not even automatically adjusting volume. So I will just talk louder. All right, so I've actually seen this robot right here working in a hotel. Literally, the device is for delivery of food from and drink from the front desk shop area, and it can be sent to a specific room. that specific room will be something that is pre-programmed in there, but the robot will be able to localize itself and find a way to get to the room, including calling an elevator, going to a particular floor, getting in and out of that elevator. I don't know how many of you have one of these devices, but they are getting rather popular in the US. It's not just the iRobot vacuum cleaner, but it is ones from other organizations. I've worked with a company called TTI Floor Care here in Charlotte, and we actually investigated the ability of localization and mapping for a vacuum cleaner under the Hoover brand. And then the one in the middle is supposedly the Google autonomous vehicle. And these are all service vehicles because they are doing things for humans, but it doesn't include industrial automation. So that's the important aspect to think about. The next classification is the industrial robot. That is some examples here. In particular, I've worked with a couple of companies that have what we call tugs or small autonomous, they're not really small, forklifts and devices that are autonomous as well that will pull materials through an industrial factory. You also have your classical robotic arm doing different tasks. In this case, it's welding. And then this here is up in the middle, towards the left-hand side, is a vehicle, or I should say, a system that will make a rebar reinforced concrete wall that might be able to autonomously build houses in different parts of the world. But again, the industrial robotics are looking at situations in industrial automation applications. Probably the one that everybody else has heard in the past or seen at least is in automobile manufacturing lines. They're used an awful lot. There is also personal care robotics. So the example that you see on the right is solving a problem that Japan has where their population is aging. And because of their aging population, they're going to be needing more robotic devices to care for the elderly. And as opposed to what it looks like, that bear-like creature is not somebody dressed up in a funny plastic costume, but it is an actual robotic device that is intended to lift elderly people and move them from a gurney perhaps to a bed. Now, the other classification is exoskeletons, which you see here on the left-hand side. And the exoskeleton is available to help those who have inability to walk on their own due to paralysis or injury to actually walk on their own with perhaps hand instructions or hand direction of that. But exoskeletons are also used to multiply the force of a factory worker, or even they've discussed it for the military. Medical devices, you may or may not have heard of the Da Vinci surgical robot, where a individual surgeon can, looking into a screen with handheld haptics interface, be able to do delicate surgery. And the device over here would be that which would allow the surgeon to look inside the patient with the cameras and perhaps do a surgery with a very, very small incision as opposed to the larger ones that were required. And because of the robotic nature of the device, all motion is dampened. So, for example, if the surgeon might shake a little bit, the robot itself will not shake like the doctor, but it'll dampen out all of the motions and make better incisions and basically help the surgeon with some of the more delicate invasive surgeries. This other one down here is a more of a psychological robot device. It's called Paro, and it's a cute little harp seal that a lot of research has been done on how helpful it is for those who might have psychological difficulties. I've actually seen a couple of articles recently in IEEE Spectrum magazine describing its use as well. And then one classification that was not included by ISO, but I included here because it is quite a bit of some of the advancement is military robotics. Everything from flying drones that do carry armaments, unfortunately, to other devices which are designed to detonate harmful bombs or something like that from a safe distance from humans. So I've covered pretty much a basics of all of robotics for the mere fact that I wanted to make sure that we have a good understanding of what my project is. And so one thing I should mention is that the vehicle is owned by the university, but originally it was provided by a company called Zapata Engineering. Hence, we have given it the name ZapataBot. And one of the first people to work on it was the son of the company Zapata Engineering. The objective for this was to pull for an all-terrain vehicle to pull a trailer with ground penetrating radar through a field that had unexploded bombs in it. Now, the reason why that was important was during World War II, in an area in North Carolina, Fort Bragg, the U.S. Army, which is the branch that actually had most of the bombing planes, did practice runs in some areas on base at Fort Bragg in North Carolina. And when bombs were dropped, sometimes they did not explode. And so they're trying to dispose of properly all of the metal, including the explosives that might be in the ground. So for safety reasons and also for monotony reasons, it's very monotonous for somebody to sit on an all-terrain vehicle pulling this trailer. They wanted this autonomous vehicle to be able to drive in a field and make sure that you checked every square centimeter in that field for anything that might be underground. So we took an off-the-shelf all-terrain vehicle. This is one from Honda. And we identified, well, if you were to go through a field and look underneath the ground, you would need to have some way of complete coverage. And so we developed complete coverage algorithms, which included identifying specific waypoints along the way that you needed to visit. And then we also had to identify, if we were to turn, what sort of kinematic motion we have Ackerman steering. Ackerman steering means that you can have the handlebars and turn it left or right, and the front two wheels move, the back two wheels don't. As you can imagine, as you're going through each of these waypoints, a vehicle, automobile, all-terrain vehicle, doesn't necessarily make 90-degree turns. Oh, let's go previously. Doesn't make 90-degree turns. It will need to make curved turns. But there may also be obstacles along the way. So if we have a lake, we obviously cannot go through the lake. So we will have to identify how we traverse going around the lake and then continuing our motion or our path traveling. With the objective is, if we go through every single one of these waypoints, then we are assured of having visited every location in the field that we're trying to measure. So our phase one was to take this all-terrain vehicle and convert it such that it could be driven autonomously, but also be able to be driven manually. And so if you think about a vehicle, and this is very close to a two-wheeler motorcycle, that you will have an engine, and it will have, of course, the need to be able to be steered. At least it's a lot more stable than a motorcycle. But you will also have braking, and you'll also have acceleration. And so we took a look at all of our major systems that we had to control. So in this case, it turned out that this vehicle has what's called power steering assist. And when a person is holding the vehicle handlebars and turning one way or turning the other way, there's actually a motor there as well, which is helping the turning of the front wheels. Because very often you're driving this vehicle on gravel or dirt, and it's a lot more difficult to turn the vehicle in this rough surface than it is in a street with asphalt or concrete. And so we found a way to be able to measure and basically hack into that control system such that we could drive the power steering motor without anybody actually doing the turning. We also introduced a brake linear actuator. So instead of pulling cables or so, we actually use this linear actuator to depress a brake pedal that would give us some minor braking. And then we also had an easy way to control the throttle. The throttle allows us to give more gas to the engine and make it speed up. Now, this vehicle has a version of gearing that is a little bit automatic steering, but we never really drive this vehicle more than 10 miles an hour. I'm trying to think of what that equivalent is in kilometers per hour, but let's see, I'll do my math. It's about 14 miles an hour, or 14 kilometers an hour. So we're not going very fast. And so from that respect, we don't really need much braking if we need to stop. If you look at the other aspects of this design, we have our, again, this is phase one. The first thing we wanted to do is be able to drive it with a remote control transmitter, and that's something that you'll see in the video coming up, or if you were here a little bit earlier, you would have seen that in the video. The remote control transmitter allowed us to later, instead of this radio receiver in here, put some sort of computer system to be able to drive the motion of this vehicle. We also added on to this LiDAR camera GPS to prepare us for being able to use this data from LiDARs and cameras and GPS to actually hit the waypoints that I described earlier. Because if we look at this situation, it's a lot easier to identify each one of these points as a GPS waypoint that we must hit, and hence ensure that we steer correctly. So again, our phase one systems changed were our throttle, our braking, and our steering. In the end, our throttle was fairly easy. Braking was, as I said, a linear actuator, and we spoofed the steering assist module because a CAN bus controller could be used to cause the motor that was manufactured in this device, in this all-terrain vehicle on its own. So let me see how well I can play this video again. So let's see, we will. my, I'm looking for my video, and my video has disappeared from things that I could share. So let me do this.
Hey, go. 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 Drive it. Sweet.
I'm assuming you all can see this.
It's like an animal.
Like we're being herded by a mechanical dog.
Yeah.
You're like Jimmy Neutron. His dog. Tighter.
I think you should drive it to the gas station. We should put air in the tires like that.
It's hard in here. Oh, I can all I've got the whole thing so far, a minute 15. But I don't like this. I want me.
Everybody's looking out there.
All right, that was the results of our phase 1, and in the end, it was very successful. All right, I believe you can see this now. So now that we have a working all-terrain vehicle, the unfortunate thing that happened is that this was all done, and because of a recession, we had to stop work, and the funding was stopped. But we still continued to maintain the vehicle and look at some additional ways that we can improve it. So time moved on, and I think I covered this already. We added some capability, for example, for complete coverage. I had a student introduce a human in the loop capability, meaning that if there was somebody, a human present, and the system that we were putting in there wanted or could not make a decision, that it would, oh, what happened there? There we go. That a video or a person could create a instruction to respond to a question that the autonomous system had with respect to, oh, here's a ravine, what should I do? Go left or right or back up? And we introduced that as well. And part of that included an experimental setup with, in this case, we do have a little turtle down here because we did it with a turtle bot, not an all-terrain vehicle. And in this case, we relied on sensors associated with this turtle bot so that it could not only detect where it was, localization, but it could also detect obstacles. And we did give it its capabilities. And in this case, we have a situation where these lines would represent ravines that we obviously would not drive into. And these large green dots represent trees, which we obviously would not drive through. And so as a part of this, if we were to program this, our AI system would go through, and when it reached this point, it would realize that it could not visit this cell, and so it would go around and go around as well, continuing to avoid all the ravines and trees where possible. So phase 2 started about 2 years ago. And so no longer did we have this need to have it pull a trailer and go through a field. We're now looking at this autonomous all-terrain vehicle to follow a path in the forest or follow a breadcrumb path in the forest, and basically, or to follow towards a specific GPS waypoint in the forest. It could be used by military search and rescue, many different types of implementations where a vehicle would be going not on a road, but in a forested area. And it's important to note that this is an all-terrain vehicle, and although it could drive on roads, the research area for vehicles driving on roads is rather crowded, and to some respect, there's been a lot of advances made, and since a lot of companies are in this field with lots of money, we wanted to find an area that did not have so much attention to it so far. And we have a vehicle that is designed to be driven in forests and rough areas like that. Now, when I mean follow a path in the forest, that would be something like a footpath. Very often here in the United States, if you get into forested areas, there will be a beaten down path through the trees that somebody could travel. And what we mean by a breadcrumb path, and that's number 2 on this slide, is that this goes back to the old Hansel and Gretel fairy tale from Grimm, where some children are going to walk into the forest, and to be able to find their way back out, they leave a small trail of breadcrumbs on the path as they go in, so they can follow that path on the way out. The unfortunate thing is that in the story, birds come down and they eat the breadcrumbs, and we don't use bread itself. We use electronic sensors, transmitters, and we rely on these electronic transmitters, which can't be eaten by birds or any other animals, to be able to provide the signal for getting into and out of a path or into and out of a forest. Now, the reason that's important is because a forest often has a very thick canopy, meaning that GPS does not really penetrate down to the ground level very well. And so having some way for somebody, perhaps a military soldier, to drop these small breadcrumbs as they're walking through a forest or a rougher area, and then have a supply vehicle like this all-terrain vehicle follow somewhat later, has advantages. So with our system design, we now have everything introduced on a CAN bus. We are introducing our GPS, compass, LiDAR, actually 2 LiDARs, one that points straight out, and then one that will be at an angle that will be and slightly pointed towards the ground, that will be able to identify ravines and holes that appear in front of the vehicle itself. We also have the steering module and the brakes, as well as the throttle on the CAN bus as well. And then there is one larger processing unit that we will use to do all of the control for this. And of course, every single one of these modules not only has a sensor, but it has a distributed processor that is able to do a lot of the measurement, as well as learning and passing along only the important knowledge that is needed by the rest of the system. This is very much akin to what we're going to be seeing for manufacturing 4.0. 4.0 is going to have a lot of smart sensors, the leaf nodes in the IoT world, and those leaf nodes will be providing information to the central controller, but they'll have the ability to do some learning, and they'll have the ability to do some processing, mostly to avoid the mostly be able to avoid the amount of communications that needs to be done. Get back over here. Here we go. So, excuse me again. As I mentioned, we have the actuators and sensors and brain synchronization. We have implemented all the modules using a Texas Instruments MSP430 F-Series microcontroller. And with that, we created a shield that handles the CAN communications, and then we're made our own wiring. And so all of our modules, which are attached to all the different important components on the all-terrain vehicle, are attached via our CAN bus. CAN, if you are familiar with it, is a very robust automobile communications protocol and electrical system. To make life easier for us as well, we created an application programming interface library that allows us to take some of our most common functions and have a common way to read a GPS signal and to get true GPS waypoints, or to with a simple command simply turn the turn the steering 12 degrees to the right, or to apply 50% throttle power to the vehicle. And so we use this API to hide the abstraction below it, so that some of the other researchers that we have working on this only need to know how they can call the throttle or brake or steering, rather than having to worry very detailed about the actual instructions, the C code that will be needed. And at this point, there is another video I'd like to bring up. And of course, I have to do some sharing and unsharing. So first thing I will do is stop the share for that. And then I will share the video.
In 2009, the University of North Carolina at Charlotte converted a Honda 4Trax Rancher ATV into a fully remote-controlled ATV. In order to make the first steps toward a fully autonomous ATV, the following subsystems needed to be developed. The operator is not controlling the throttle, but instead having his finger on the kill switch. Here, the ATV is pre-programmed to drive forward at full speed for a predetermined distance. The rider on the ATV is not controlling the vehicle, but instead positioned to shut the vehicle off in case it were to venture off course. Here, the ATV is pre-programmed to drive backward for a predetermined distance. Lastly, the ATV was pre-programmed to follow more complex patterns, such as a figure 8. As mentioned before, the operator that is following the ATV is not controlling the vehicle, but instead is there to kill the program if anything were to go awry.
Okay, so what I've shown you now is phase 1 and phase 2. So now we have an all-terrain vehicle that is not controlled by a radio anymore. We're able to give it simple instructions on turn left, turn right. You notice we did a lot of turning backwards. At that point, we hadn't fixed some of the steering problems that we had, but we have that fixed now. So our phase 3 is now to try and drive autonomously a vehicle in a forested area on, at this point, an asphalt paved path. Our phase 4 is going to be a dirt path, and our phase 5 is going to be a paved path that will actually require some sort of obstacle avoidance like trees. So we're going to be running with Ross. We're going to have segmentation, inverse reinforcement learning. We have mounted a camera on top of our, or at the front of our vehicle. And we are gathering data with these, with this camera of a correct way to drive on a path. And in this case, you notice he's way at the edge, an incorrect way to drive on the path. And then we're validating this with, first of all, with other drivers that are manually driving to identify, or to make sure our system will correctly identify how well the driver is following the path. And then we're going to turn on the, oh yes, we will now allow this vehicle to drive without anybody sitting on it, have it drive on its own. So with any machine learning instance, you are going to first collect data, and we're going to run it through our learning systems. Specifically, we needed to do semantic segmentation to be able to identify what is the path and what is not the path. And through that, we are able to identify, if you look in here carefully, we are able to identify 3 different regions: the path itself, the off path, but no obstacles like trees, and then the off the path with things like these forested trees, leaves, etc. Keeping in mind too that we are then also looking for the edges of the path, and that will allow us to identify how to stay within the path. So we are giving this path using inverse reinforcement learning, different way to identify how we should steer the vehicle. We're always assuming right now at this phase that we are driving on a flat surface with a constant speed, and the only thing we have to control is the steering. Do we steer left a little bit? Do we I'm sorry, are we in an area that's not so desirable to the left, or are we way off to the left outside? Or are we on the right on the inside? It's not as desirable. Or are we on the right on the outside? Totally undesirable. And based on that, it will give us our instructions on how to steer, because our objective is to be here in the center. And so throughout our experiments with taking data and driving, we were able to identify paths and when we are on and off. And that leads us to yet our 3rd video. And I can't forget to share.
In 2009, the University of North Carolina at Charlotte converted a Honda 4Trax Rancher ATV into a fully remote-controlled ATV. Recently, the ATV project has been picked up again with the hope to enable autonomous driving. In this clip, the ATV is pre-programmed to drive backwards for a predetermined distance. Once simple maneuvers were working at a satisfactory level, the ATV was given more complex paths to execute. Here is an example of the ATV driving backwards autonomously. In the previous videos, the ATV has had no way to see or sense its environment. This is where pathway identification comes into play. Here is our proposed solution and implementation to enable the ATV with pathway identification. First, 2 cameras were mounted onto the ATV. Second, an expert driver drove the ATV at a constant speed in the center of a path. While the ATV traversed the path, the cameras recorded and stored the data into a file. The data was processed using semantic segmentation, which can be seen here. The process video that you see on the right is broken up into different classes. For example, the purple indicates the path, while the darker green indicates the trees, and the lighter green represents the ground outside the path. Once the semantic segmentation of the video is complete, an inverse reinforcement learning model is used to identify the different sections of the path. As seen in the figure, the path is broken into sections, which consist of left outside, left inside, center, right inside, and right outside. The learning model uses these distinctions to help indicate rewards. Once this was put into place, more data was gathered where the driver drove off the path. Semantic segmentation was applied and can be seen here. Going forward, more data needs to be collected, and the plans are in place to make this happen. However, when the new data is recorded, we will also be recording the angle of the handlebars, which will be used in conjunction with the video footage.
All right. So I'm almost done. In fact, I am done. So my discussion and conclusions are, if you think about some of the ideas and skills that we have used for our autonomous all-terrain vehicle, you can see how that is actually using machine learning, artificial intelligence and intelligent sensors, Internet of Things, to be able to represent very similar to what Manufacturing 4.0 is going to be coming up in the next few years. I would like to thank you for your time. And again, as I said, hey, here's the picture of me petting that cow. By the way, that's been on the back of a lot of my presentations because it's such a fun one. This is my my contact information, including my webpage. With that, thank you very much.
Thank you, Jim. That was a wonderful experience. We ourselves felt like traveling in your ATV. All the videos were wonderful and really very inspiring presentation, because this is what is going to be the future. And I request the participants to discuss with him if you have any doubts or any clarifications. You can
good evening, Professor James.
Yes.
Yes, I am Shanmugha from College of Engineering, India, Anna University. I'm quite impressed by the way that you have been into the product development of the future, and looking at a country where we have a large-scale agriculture, where this is going to be of prime importance, as you say. And of course, apart from that, it's not going to stop with just agriculture, but it may be extended to your military and what all kinds of stuff. And there are 2 types of vehicles that are taking up. One are the drones of various sizes, starting from the miniaturized to the large ones. transporting even the patients. And the second one, people are talking about the autonomous levels of the transportation. So, in what level of this autonomous? Because they say level 1 autonomous, level 2 autonomous. So, when will this be completely autonomous? If it is connected to the real-time data, or as we travel only with the already pre-programmed path? How do you clarify and how do you classify these kind of things?
Well, first of all, you know, being that we're not on a road,
Okay.
a lot of the discussion of the levels of autonomy up to level 5, full autonomy, not quite exactly the same, although a lot of the capabilities are the same. Let's put it this way: I think it's much easier to drive on a road. Well, let me. It's much easier to drive on a road in the U.S. than it is to drive on a path in a forest.
Definitely.
Now, all bets are off. All bets are off when you're driving in India. I've been in vehicles. I've never driven in India. I will never drive in India. I think all of you are so brave for being able to do that.
All experts, Jim.
I fully think autonomous cars will have great difficulty in India unless all the cars are autonomous. All right. So again, getting back to all the different capabilities of the levels of autonomy. We're shooting for level 5. Here's a waypoint. Go and get there. And the difficulty in a forest is that it's not as well known as streets. There's lots and lots of pictures of streets that you could use in your machine learning interfaces to know, okay, here is a stoplight expected. Here's a stoplight expected. Here's a stoplight expected. And then you have to worry about obstacles like people, bicycles, cows, dogs, etc. As opposed to in a forest where you don't know a priori really where a tree is. You just have to, or for that matter, you kind of know where ravines might be because you will have an idea of the undulation of the landscape, but it will be a little bit harder. And so from that respect, you can't program that. That's where machine learning comes in and helps. And that's what a lot of these autonomous delivery vehicles, autonomous vehicle drones, etc., they're finding is that you have to leave a lot of the control to the machine learning.
Okay.
Did I even answer your question? I should say.
Yeah, sure. Okay. Yeah, that's right. Thank you. Thank you.
Jim, can you stop sharing the screen so that we can see you on the big screen?
All right, let's do that. Yeah, because I'm doing all this stuff and nobody can see it when I do that.
And I would like to welcome Dr. Van. How are you? Thanks for coming to our webinar.
Hi. Hello. Hi. Can you hear me?
You can turn on your video. You can talk to Jim.
It's okay. I just came back from work. Yeah, it's already almost 9 o'clock at night in Malaysia.
Jim, she's from Malaysia, Jim. Yeah.
Yes.
Van,
Yes.
you can talk to him.
Oh, okay. Congratulations. Nice to see about your ATV and it's autonomous. We haven't started yet. I think I saw you are from electrical engineering. I'm from mechanical actually. So, but I know in UITM also we also started with autonomous vehicle, but just going around the campus. It's just like a train.
She's head of transport in UITM Malaysia, Jim.
Mm-hmm.
She's very much interested to attend your session.
Thank you.
Yes.
All right.
Maybe
so,
I contact Prof next time.
Okay.
I get the email address.
Oh,
thank you. We did have a question online, and Ramesh G says, what is the difference between machine learning and deep learning? And this is where I have to say, oh my gosh, I don't know. And this is one of the things about being a faculty member is when I got my my master's and my PhD and my bachelor's, there was no such thing as machine learning, period. And so this is a new topic which I'm just now getting into. And so to answer the question, I think deep learning is a subset of machine learning. There are different algorithms associated with it. And that's some of the effort that I'm going to be doing over the next year is actually learning more and more about what deep learning is and machine
You need to
learning.
learn deep to learn deep learning.
Yes, I need to spend some more time getting deep into learning. So the answer is, I don't know.
Somebody has asked you to explain about the CAN bus in phase 2.
Okay. CAN bus is an automotive differential signal bus that is used pretty much in all new cars that are being manufactured nowadays. The reason why it's so much nicer than just a regular set of twisted pair is because on one of the wires of the communications there is a negative signal and there's a positive voltage signal on the other wire. And in specifically, we're using the CAN bus. It's a communications bus. It runs at a speed somewhere between 500 and 1,000 kilobits per second for our system. And we use it because it's very resilient to electromagnetic disturbances that might occur in the vehicle due to the alternator, and that's a reason why it's used in a lot of vehicles. So it's nothing more than a communications wiring. We could have used Wi-Fi or Wi-Fi or any wireless, but we wanted to do something that was a little bit more robust and more automotive-like. And so did that, Maddie, did that explain your question in enough detail about the CAN bus? And while we get a response.
Have you cleared your doubt? Yeah, she's
okay. Says thank you. And share the PowerPoints. And so I will share with Dr. Eswaran the PowerPoints that I just created.
Yeah, sure. Jim, I'm very keen to know about your university, like how the classes will go on and how many students will take part in researches like this, how many UG, PG scholars you have in your team.
All right, so at the University of North Carolina at Charlotte, we have approximately 4,000 students in the College of Engineering. The university itself has 30,000 students. In our department, we have about 1,000 students. And working on my team alone right now, I have about 6 students. This is not the only project that I'm working on. I have other ones that include localization of a robot based on RF signals, that beacons that serve as RF signals. And I also am working on potentially, of all things, a robotic guide dog to assist the blind. And I'm working with another company on a UV sanitizing robot for hotel rooms.
Oh.
So we're looking at all different robotic applications, and almost always it's robotic applications, because in the end, I almost hate to say this with some mechanical engineers on the phone or on the call, but a lot of the interesting and complex problems are not going to be mechanical and actually not be electrical, but they're going to be software related and solution associated with it. So it's going to be more of taking subsystems that are already solved and putting them together. By the way, when I provide the PowerPoint slides. I'll actually put in a link to the YouTube videos. However, there is one video, the one all the way at the end. I think I'll just upload it and make that YouTube as well.
Yeah. So that was wonderful, Jim. We have brought you to India during COVID. You just escaped from India and you're back again to India. So we are looking forward to have you personally, physically present here after all these things get sorted out. And I think we can have a virtual photograph. I request all the participants to switch on your, turn on your video, please.
Let's see. I guess that's not working all that well. A lot of shy people out there don't want their picture taken.
Yeah, please turn on your video. All are working from home, Jim. They are not dressed up.
I could imagine. So, you know, one thing that has been mentioned, I have been to India, as I said, 6 times, and you know, my university won't actually pay for me to visit India. So, if somebody wants to cover my flight and local arrangements to India, I'd be happy to come. And I have done that several times. I've actually given talks at anywhere between 20 and 25 different universities and schools in India during all these visits, several of them several times. So.
Yeah. Can you all switch on your video, please? Yeah, smile. Yeah, one by one, everybody is turning on the video. Please turn on the videos, please.
I like some of your backgrounds, by the way. Yeah, with the Zoom aspect, I actually I could describe the thing that's behind me if you're interested.
Yeah, you were telling about the whiteboard, Jim.
Yeah, this is not a whiteboard. It is a light board.
Light board. Okay.
And so I stand behind this. I could move off to the side so you can see it. It's a piece of plexiglass, and you notice there's a dark background behind it. And I'll take nothing more than my iPhone, and I'll record video of me writing on that piece of plexiglass with a fluorescent whiteboard marker. And because I have LED lights underneath the plexiglass, the letters that I write and the drawings that I put on that really pop up. And so if you were to actually Google the concept of light board, L-I-G-H-T board, you'll see a lot of what that is. And so since we're all teaching from home as well,
yeah,
that's one of my instructional techniques.
You had a video, right?
Yeah, I could show that if you're interested in that.
Yeah, yeah, please.
I will have to go to.
Thank you all for the the photograph. Let us see the video from Jim.
And that will be the last thing I have.
Yeah.
All right, here's where I got to figure out what's the easiest way to share. I got to move this off to the side.
But this is a test to make sure that the whiteboard looks pretty good. I've changed focus. I'm kind of playing with this a little bit, but my aim is and I'm happy to do this sample video for you.
So I assume you saw that, right?
Someone has raised hand. Would you like to talk something? Okay. Well, Jim, I think it's time.
All right. Well,
Yeah.
I'd like to thank you all for attending this, and I hope this was a good inaugural session. And I do urge you all to attend all the remaining ones that will go on over the next few days.
Yeah. Thank you, Jim. Thank you, all the participants. We'll see tomorrow evening again. Thank you. Stay safe, Jim. And my regards to your daughters.
Oh, yes.
Okay, then. Bye.
Bye. See y'all.
Bye.
As we say, see y'all.
Virtually.